Hello. So today what I would like to do is to talk about calorimetry. And this is sort of the last of the major topics, has several different types of problems. We're going to look at calorimetry today. So calorimetry is essentially the science or the technique of measuring heat transfer. Is in calories, right? So we're going to measure heat transfer. What we said was that if we have an object that's hot and we have an object that's cold, heat will flow in the direction from the hot to the cold. Okay. That's essentially what we observe. And so if a chemical reaction is occurring, so let's say we have our cylinder here and there's some gases in here that are reacting with piston, and then we put a water bath around it. If the reaction is exothermic, it will release heat into the water. So if it's an exothermic reaction, so Q is negative, and so is delta H, right? So if it's exothermic, then that means the heat is transferred to the water. If, on the other hand, the reaction is endothermic, then we'll find that heat goes from the water into the gases. So for endothermic, Q is positive or delta H is positive. You can use heat or enthalpy changes. And we would say that heat is transferred from the water or to the gases. Okay, so endothermic, exothermic, those are our two choices. What none of our discussion has done, though, we have not seen how to actually calculate the heat. So we have a way to calculate work, right? But how do we calculate heat? It's actually very simple. It has to do with temperature. Temperature is a measure of how much kinetic energy molecules have. So the higher the temperature, the more kinetic energy those molecules have. The lower the temperature, the less kinetic energy they have. So heat transfer can be measured by measuring temperature. Okay. So imagine it this way, just, you have this mass, it's an object, it's a mass, and heat flows out of it. Okay. We can calculate how much heat flows out of the mass through a very simple equation. It's M for mass times C for specific heat capacity times the final temperature minus the initial temperature of the mass. Okay, so we measure the temperature at the beginning, Ti. We measure the temperature at the end, Tf. Take the difference between those two, that's the change in temperature, and we multiply that by these two quantities. So Q is the heat transferred. M is the mass of the object. That's easy to measure, right? C is called the specific heat capacity. Of the mass or of the object. Okay, I guess I'll say object since I did for the previous one. Now, the specific heat capacity may or may not be known. There are some problems where we don't know it and we try to figure it out. You can figure it out experimentally. Or we may know what the material is and we know what the specific heat capacity. Each material has its own specific heat capacity. Water, for example, is 4.18 or 4.184. Copper is around 0.385, right? So each material has its own specific heat capacity. In general, metals have heat capacities, specific heat capacities less than 1. And non-metals, meaning molecular substances like water or alcohol or fats, generally have specific heat capacities of 2 or greater, 2, maybe 2.5, all the way up to about 4 for water. Water has a specific, very high specific heat capacity over 4. Okay, we can look those up. You can do a Google search, type in, specific heat capacity of ethanol, specific heat capacity of wood, specific heat capacity of gold. There, of course, is a set of table values in the ALEX software as well. So it's actually a very simple equation. All we need to do to calculate the amount of heat is measure the mass, look up the specific heat capacity, and then measure the temperature at the beginning and at the end of the heat transfer. And that will tell us how much heat was transferred through. Okay, so let's take a look at a couple of problems involving this equation. The ones we're going to look at are generally for constant pressure. Okay, so let's see. Okay. This one is calculating the specific heat capacity, C. By the way, some textbooks use an S. The Burge textbook uses an S for specific heat capacity. You can imagine why, right? Specific, so S, but typically it's a lowercase c. A chemist carefully measures the amount of heat needed to raise the temperature of 428.0 milligram sample of pure substance from 32.2 degrees Celsius to 54.3 degrees Celsius. The experiment shows that 39.5 joules of heat are needed. What can the chemist report for the specific heat capacity of the substance? Round your answer to 3 significant digits. So they give you the mass, they give you the initial and final temperature, they tell you how much heat is transferred, and then they ask you to find the specific heat capacity. Pretty straightforward, actually. You just have to take the equation and just rearrange it. So heat Q equals M mass, C specific heat capacity, change in temperature. So change in temperature is T final minus T initial. I for initial, right? Or T2 minus T1, if you want to use the notation. So we want to know the specific heat capacity. So we divide both sides by M. And we divide both sides by delta T. And you get heat over mass delta T is equal to C. So I'll rewrite it down here. C is Q for heat over M delta T. And what do we have in here? We have some numbers. So the first one is the heat is in 39.5 joules. The mass is 428. I'm going to write that down here. 428.0 milligrams. Milligrams, all right. And the initial temperature is 32.2 degrees C. And the final temperature is 54.3 degrees C. So typically, the specific heat capacity is per gram, sometimes per kilogram, sometimes per mole, but very rarely is it per milligram. So what I'm going to do is I'm going to convert this milligrams into grams. So milli is 10 to the minus 3. So there's your milli, and then there's your grams. Okay, so I'm going to put that into grams just so that we don't have the milli floating around in there. And then your change in temperature is 54.3 minus 32.2. Okay, and there you go. So let me grab my calculator here. So 39.5 divided by 0.428 divided by, that difference in temperature is 22.1. What do you get? You get about 4. 4.18 The units are joules divided by grams divided by degrees C. And those are typical units. Looks like it's water. It looks very much like this is water. It says a sample of a pure substance. This is very close to water. Okay. And again, you can look those values up, 3 significant digits. Now, if you had left it as 428 times 10 to the minus 3 or 428 milligrams, you would just have, it would be 0.00418. Actually, is that true? We'd be dividing it by a bigger number. So 0.00418 joules per milligram degrees C, but most likely the Alex software told you what units they wanted it in, and they would most likely want it in grams. So that's why I did that conversion. Okay. So there's a specific heat problem. That's the specific heat. Now, conceptually, the specific heat capacity, so C, specific heat capacity. Sometimes people just call it specific heat because it's such a long name. The term specific generally means per mass unit. So see how we divide it by mass? So we have mass units in the denominator. So if something is per gram or per kilogram, it's often referred to as the specific quantity. So specific heat capacity right here. So the specific heat capacity is essentially how much heat it takes to raise 1 gram of a substance 1 degree C. So what this says is if you had 1 gram of this water and you made its temperature go up by 1 degree C, like from 21 to 22 or 23 to 24, it would take this much heat to be able to raise the temperature of that water by 1 degree C. Now, obviously, if you had 10 times as much water, then we would have 10 times the mass, and that would require 10 times the heat. So really what we're doing in this problem is we're taking a mass that they measured, temperatures that they measured, heat that they measured, and then figuring out what it is, how many joules of energy, how many joules of heat would be required to make 1 gram of this substance increase its temperature by 1 degree C. And that's called the specific heat capacity or just specific heat. Okay. Let's take a look at another one that is very similar. And you'll see that it's pretty similar. It's actually even perhaps a little simpler than the one we just looked at. Using specific heat capacity to find heat. So now we're going to find heat, Q, right? Q is heat. Calculate the energy required to heat 118.0 milligrams of water by 40 points from 40.7 degrees Celsius to 53.9 degrees Celsius. Assume the specific heat capacity is 4.18. See how they call it joules per gram. Remember, -1 means per divided by grams. And then there's a symbol here, K for Kelvin. You have to go back perhaps all the way to chapter 1 to go back to the units. This is called a Kelvin. It's a temperature unit. For our purposes, it's going for this calculation, for this set of calculations in chapter 5, it's equivalent to the degrees Celsius. So that's not an issue. We could also write this as 4.18 joules per gram per degree Celsius, and that would be fine. Okay, rounded to 3 significant digits. So notice what they give us. Initial and final temperature, there's your delta T. They give us the mass, there's your M. They give us the specific heat capacity, which is C. And then they want the heat, that's Q. So they're giving us everything that's on the equation except for Q. So Q equals MC delta T. And so that is going to be, what was the mass? The mass was 118 milligrams. Again, same thing here. I'm going to write all these down just so you can kind of look at it. And then I'm going to put the final temperature. Remember, it's final temperature minus initial. Okay, so Q is going to be positive. That means heat was transferred to the substance there. Okay. So same kind of thing, we're gonna end up with millijoules. If the answer that they wanted was in, say, millijoules, then that's fine. We'll leave that as it's milli. But if they want it in joules, we'll convert it. So I'm gonna, take 118.0 milligrams. And again, milli is 10 to the minus 3. So it's just 10 to the minus 3 grams, 118 times 10 to the minus 3. So now, what about this here? Again, the idea is, I'm not going to go through this in great detail. We're going to cover it more in chapter 10. We'll deal with the issue of Kelvin, but just very quickly, if delta T is 1 Kelvin, then it's also 1 degree C, and we'll cover that in more detail. So for these problems, you can just put in degrees Celsius there so it's consistent with these ones here. So that means that Q is 118 times 10 to the minus 3 grams times 4.18 joules per gram degrees C. And then our temperature change, it looks like it's around 13.2. Oops. Is that right? 3 minus 0, so 13.2. And take a look, the degrees Celsius cancel. The grams cancel, and you're left with joules, which should be our energy units, right? It should be joules. So Q equals, let's take a look at this, times 4.18 times 13.2, and you get, is it really that small? It might be, it's pretty small, right? 0.118 times 4.18 times 13.2. It's actually pretty small. It's only about 6.5. 6.51 joules. That would be our units that are left there. Okay. So very similar to the previous problem, right? The difference here is that instead of finding C, you're finding Q. But, this is the same kind of idea. You're just manipulating the equation. Okay. So let's take a look at using the specific heat capacity to find the temperature change now. So I'm going to bring this one up here. These are all very similar problems. I could probably just skip all of them and move on to the next topic, but it's not a bad idea for you to really get good at these. Okay, a chemical reaction takes place inside a flask submerged in a water bath. Remember, think of our gas cylinder problem. The water bath contains 3.40 kilograms of water at 25.7 degrees Celsius. During the reaction, 52.2 kilojoules of heat flows out of the bath and into the flask. Calculate the new temperature of the water bath. You can assume the specific heat capacity under these conditions is 4.18 joules per gram per Kelvin, right? Round your answer to 3 significant digits. So notice in this one, again, you've got, you have an initial temperature. They're telling us how much heat is flowing in. We have a mass of water, and then they want us to find the final temperature, the new temperature, which would be the final temperature, given that it's got this value of C, specific heat capacity. Okay. So let's take a look at this one. It's a little more involved, but not really. To be honest with you, it's really the same kind of idea. Q equals MC delta T. Now, remember, delta T is T final minus T initial. Okay, so if they're asking us to find the new temperature, they're asking us to find the final temperature. So algebraically, the order that you do the operations is kind of important in order to simplify things for yourself. So if we just wanted to find the change in temperature delta T, what we would do is we would divide both sides by MC, right? So that means that Q over MC would be delta T. But delta T is T final minus the T initial, right? So if we want to find just T final, which this question is asking for, we would add T initial to both sides. So let me write it this way. T initial plus Q over MC equals T final minus T initial plus T initial. See what I did algebraically? I'm adding T initial to both sides over here and over here. So that's cancels and you got T final, okay? So if you want to find T final, you just got to take Q over MC. I'm just writing this in different order, plus T initial. Okay. And, you know, there is an issue of units in here. So they give us, for example, that Q is 52.2 kilojoules. The mass, however, is in kilograms. That's kind of cool. That's useful. And then our specific heat is it's water. So it's 4.18 joules per gram degree C. See how I put degree C there because it's the same as in Kelvin. And then our initial temperature was 25.7. Okay, so this is the water bath problem. It's the problems that we were looking at in the last couple of sections. You've got, you know, some cylinder. They called it a flask, but that's fine. Here's your gases. It's in a water bath. So there's water in the water bath, right? So the reaction produces heat. That heat goes into the water, right? So what happens? The temperature of the water is going to start off at 25.7 and it's going to go up, right? It's going to go up because heat is flowing into it. How much does it go up by? Well, it depends on how much heat there is. The more heat you put in, the hotter it'll get, right? So that makes sense, right? The more heat you put in, the bigger that term should be. The more massive it is, the less it's going to go up, right? If you put a certain amount of heat into a thimble full of water or a little cup, it's going to get hot. But you put the same amount of heat into a bathtub full of water, it's not going to get that hot. It'll go up a little bit, but maybe not that much. So we divide by the mass. And then it also depends on the specific heat. The higher the specific heat, the more energy you got to put in to get it hotter, okay? For those of you that are engineers, you're really going to look at this when you do thermodynamics in your engineering course, where you'll see that like this specific heat is important. And for water, it's really important, okay? So our final temperature then, take a look at the units. I didn't get rid of the kilo because I saw that that kilo is going to cancel and the joules here will cancel and the grams here will cancel. And so you're left with 1 over degrees C, which is the same as degrees C. So you're adding degrees C. Remember, apples to apples, oranges to oranges when you're adding. So there you go. So you just got to add those two terms together. So 52, by the way, you could convert the kilojoules into joules, multiply by 1,000, that's fine. But you would also need to convert the mass, 3.40 kilograms, into grams and multiply that by 1,000. So you'd be multiplying the numerator and the denominator by 1,000. So, you know, you do that, it's not going to make a difference. 52.2 over 3.4 over 4.18. So this first term is pretty small. It's 3.67. And then you're going to add that to the second term, which is 25.7, right? That's the initial temperature. So 3.67 plus 25.7, and then round it to the near, what do they say? Round it to the nearest, you have to be careful. Round to 3 significant digits. Okay, well, 29.4 degrees C. Okay. And there you go. Went up about 3.5 degrees, 3 2/3 of a degree. There you go. Okay. Okay, one more here I want to look at is now we're going to do the molar heat per mole. I mentioned a little bit earlier that sometimes we do it per gram, per kilogram, or per mole. The molar heat capacity is per mole, okay, as opposed to per gram. And generally the molar is going to be a smaller value, right? Is that right? No, per gram, it'll actually be a bigger value, I guess, right? Because the number of moles would be smaller, so it'll be a larger value. It just differs by the molar mass. The difference between grams and moles is, you know, the molar mass. A chemist carefully measures the amount of heat needed to raise the temperature of 341.0 milligrams sample of C4H8O. Notice how they give you the chemical formula here. That's so that you can calculate the molar mass. From minus 3.8 degrees Celsius all the way up to 10.5. So that's a delta T of about 14.3 degrees Celsius. And it's positive, right? We got hotter. The experiment shows that 8.18 joules of heat are needed. That's your Q value. What can the chemist report for the molar heat capacity? Okay, so what I'm going to do here, you can take a look at this. See how we have our delta T, we have our Q, we have our M, although that's in milligrams, and we'll need to convert that. That would let us find the specific heat capacity. That would get this, we looked at that problem, right? Just take a look at it. But this one is asking for the molar heat. So here, there would be different ways to approach this, but what I'm going to do is I'm going to step one, I'm just going to find the specific heat, capacity. I'll put that in parentheses, in quotes, because specific heat is short for specific heat capacity. So how do we do that? Well, Q equals MC delta T. So C would be Q over M delta T, right? So you would do it just like we did before. Let's do that first, okay? So let me, sorry, kind of hit it here. I'm going to write the numbers down here. The mass is 341.0 milligrams, which again, in grams would be 341.0 times 10 to the minus 3 grams, because milli is 10 to the minus 3. Centi is 10 to the minus 2. The temperature, so delta T. Hopefully you got that down. It's final minus initial. So that would be 10.5 minus 3, minus a minus 3.8. It's going from a negative temperature. So that would be 14.2 degrees C, okay? So you got your delta T, and then they tell you the heat is Q, 8.18 joules. And then they want you to find C, okay? So we've done that already, right? That's not hard, so let's go through it, okay? But now what I'm gonna do is, well, let's do it first. So C is Q over M delta T. Like I said, the order that you do this, it doesn't really matter, but there's a different way to do it. So 341.0 times 10 to the minus 3 grams. And then your delta T would be 14.2 degrees C. This is just going to give us the specific heat capacity, just like we've done this already. So 8.18 over 341 times 10 to the minus 3 over 14.2. And it's, again, you should get these values that are like less, 4 for water, 2 for alcohol. And the units would be joules per gram degree C. Okay. Now, there's your specific heat capacity like we've done before. But the thing that's different is they want the molar heat capacity. Okay, we're not talking about teeth, we're talking about moles, right? So the compound, you have to know the formula to be able to do that. So that's why they tell you they actually don't tell you what it is. They tell you it's C4H8O, which I assume is probably butanol. It's probably an alcohol with an OH on there somewhere, okay? But it doesn't really matter. So what I'm gonna do is I'm gonna calculate the molar mass, okay? So 4 times 12.011 grams per mole, 8 times 1.00794 grams per mole, 1 times 15.9994 grams per mole. I'm getting better at memorizing these numbers, at least for the hydrocarbons. 4 times, actually it's 12.0107. Let me put that in there, 12.0107. So let's do that correctly. 4 times 12.0107 plus 8 times 1.00794 plus 1 times 15.9994. So your molar mass is 72. I guess I'll go out 3 significant digits, 106 grams per mole. Okay. So now I'm going to write this as 72.106 grams equals 1 mole, right? That's how we did it back in chapter 3. Okay. So now look at how I do this. 1.689 joules per gram degree C. So I'm going to put 1 mole down here and 72.106 grams up here. Why am I doing that? Because I want to convert the grams to moles. So if I put the gram up here, the grams will cancel, and now I'll have moles at the bottom. So in order for that to work, I got to multiply by the 72.106. So it's about 122. Yeah, that's about right. It's 122, 3 significant digits. Now it would be joules per mole degree C. And this is called the molar heat capacity because it's not per gram specific or kilogram. It's per mole. Per mole is called molar. So if you're dividing by moles. So how did I do that? I just figured out the molar mass of the substance. And then I use dimensional analysis, which most people don't want to use dimensional analysis. They'd rather just sort of guess at the units, but that's what's going to get you the right answer here. You write it as an identity, this equals that. And then you put the one in the top that's going to get rid of the grams, and you put the one on the bottom that's going to give you moles in the denominator, which is what we want. So molar heat capacity, molar, should be in joules per mole degree C. Specific should be in joules per gram degree C. Mass in the denominator as opposed to moles in the denominator. Typically joule. I mean, you know, to be honest with you, though, it depends who you talk to. Physicists or engineers sometimes use kilojoules per, because this would be 0.122 kilojoules. And sometimes people want numbers that are less than 1 or around 1, as opposed to numbers that are in the hundreds. It just sort of depends on the culture of who's doing the problem. Okay, and there you go. Last problem is called solving a basic calorimetry problem. This one's a little more involved, but so I'll show you this one. I think there's another one that I did, or 2 perhaps, that I did last semester that you can also refer to those. And you can go back as far as you want. I've done it many times. Solving a basic calorimetry problem, 59.5. So look at the picture first. See how this is kind of a little bit like our gas cylinder problem? Okay, it's a little bit like it. In this case, it's not a chemistry problem. So we could put a chemistry problem in there, but that's really what you're doing in the laboratory part, is doing the chemistry problem. This is really a physics problem. What they do is they take an object, a sample, piece of rock that's not going to react chemically. You're just going to put it in water. It starts off really hot. The water is at room temperature. This is hot, so it transfers heat to the water, so the water gets hotter. And really, they're just having you use the calorimetry equation, Q equals mc delta T, just to figure out how much heat flows and what the final temperature is going to be. So it's not really a chemistry problem. But if we did a chemical reaction in here, it would essentially be the same phenomenon. Okay, it's just a question of where the heat's coming from. For this, what they do is they take the object and they put it in hot water, boiling water, till it reaches a high temperature. Then they throw it into the room temperature water. Okay. They give you the mass of the glass. Okay, so that's that sample, which is that glass. It's got 300.0 grams of water. There's your mass of the water. The sample starts off at 87.8 degrees C. The water starts off at 15.0 degrees. That's kind of cold. 15 is a little chilly. When the water stops changing temperature, it stops at 17.2. Pressure's at 1 atm. We don't need to know the pressure. That's just telling us that we don't have to worry about any work being done. Calculate the specific heat capacity of the glass. We know what it is for water, 4.18 joules per gram degree C. We're just going to find it for the glass. Okay, so a lot more numbers in here, or a few more numbers in here, but no problem. Let's take care let's take a look at this. Oops, sorry. I made a mistake. I didn't show this to you. So all that words I just put, that's for this, okay? Sorry. So there's the glass. It's in the water. The water's 300 grams. You have an initial temperature of 15. It's going to go up to some final temperature. It's not going to be 1,000 degrees, and it's not going to be under 15, right? The glass is already hot, so it's going to transfer heat to the water. The glass will get cooler. The water will get hotter, and then they give you the mass of the water, the mass of the sample. Specific heat capacity. Actually, they tell you the final temperature is 17.2. Calculate the specific heat capacity of the glass, the sample. Okay, so there's your picture there. Sorry, I didn't have that up there earlier. Okay, I'm going to show you how to solve a basic calorimetry problem. There's more involved ones, but we're not going to do them in this course. Essentially, the idea is this, and I'm just going to make a little cartoon here. So here's your hot object, which is the sample. Here's your cold object, which is the water. Remember, if something's hot and it's in contact with something that's cold, we call that thermal contact. The heat will flow from the hot to the cold, right? The question is how much? Well, interestingly enough, it's going to be equal to the mass of the hot object times the specific heat of the hot object times the change in temperature of the hot object. That's how much heat will flow out of the hot object, mc delta T. But what about the cold? So this is H for hot. For the cold substance, it's just going to be equal to the mass of the cold times the specific heat of the cold times the change in temperature of the cold. But there's one more point, and that's linking those two together. If the heat is going from the hot to the cold, the heat has to be the same, right? Now, obviously, that might not be true. There might be some heat loss somewhere, but we're assuming that the heat is going from the hot to the cold. So that means these two are equal to each other, right? The amount of heat that goes out of the hot is the same as the amount that goes into the cold, except there's a difference. One's gaining, the other one's losing. So there's a negative on one side. It really, in a sense, doesn't matter which side you put on, but since the hot is losing the heat, let's put the negative on the hot part, on the hot side. Oops, sorry, this is a cold. It doesn't really matter as long as you have them being opposite. Really what we're saying here is Q hot plus Q cold is 0. Two of them added together have to be 0 because we're not creating any energy, right? We're not creating it. It's just being transferred from the hot to the cold. So mathematically, QC would just be minus Q hot. Okay, but we have these equations here. And notice we know the mass, we know the change in temperature, we know the mass, we know the specific heat, we know the temperature change. The only thing we don't know is right there is C hot. Okay, so let me go through this. What I'm going to do is I'm going to first do the water. Okay, so the water, again in grams, it's in grams, is 59.5 grams. Specific heat of water, memorize this number, 4.18 joules per gram degrees C. The change in temperature, final minus initial, okay? So it started at 15 and it ended at 17.2. Okay, so that's a difference of 2.2 for the water. So 59.5 times 4.18 times 2.2. So you get 547.16 joules. Why joules? Degrees C cancel, grams cancel, joules. So that's how much heat went out of the water. Well, Q of the hot is minus Q of the cold. So Q of the sample is minus Q of the water, right? The water was the cold substance. So that would be minus 547.16 joules. So that's your Q value for the sample. So Q sample, which is made out of glass, they say, is minus 547.16 joules. And that is equal to the mass, which is 300. Ooh, I am so sorry. I made a mistake. I got the mass wrong. The water was the 300.0. I am so sorry. So the water is 300. I got the two mixed up. Okay, so let me recalculate that. $300 times 4.18 times 2.2 is 2759 joules. Okay, and then so this would be minus 2759 joules. Minus 2759 joules, right? So the glass is going to be negative, and that, I have a little more room here, is the MC delta T. So 59.5 grams times C times, now this is where you might be confused. What's the temperature change here? So the sample, it starts off at 87.8 degrees C. And they don't tell you the final. But here's the thing. If it's in the water and the sample are going to come to the same temperature. That's when heat flow will stop. So that means it's still got to be 17.2 degrees C. So delta T is 17.2 minus 87.8. Now that's going to give you a negative number. Okay, you're going to get 17.2 minus 87.8, but that's because it's getting colder. If something's getting colder, it's going to be a negative change in temperature. Okay, let's make sure that you're seeing this. There we go. Okay. Make this a little bit bigger for myself so that we can see it. Okay. There we go. Okay, so minus 70.6 goes here. So we have the mass of the sample, the change in temperature of the sample, and the Q of the sample, which is negative. Okay. Now, what can you do mathematically? If you have a negative value equals a negative value, you can multiply the equation by -1 and make it positive, right? So let's do that. Let's multiply everything through by -1. And we have 2759 joules equals 59.5 grams times C times 70.6 degrees C, right? So I eliminated the negative here, and I eliminated it here because it's negative on both sides. So multiply everything by -1. So now I'm just going to rearrange this by saying, look, we want to divide both sides by mass and divide both sides by delta T to give us C. So 2759 joules over 59.5 grams over 70.6 degrees C. That's going to be C, right? This is C of the sample, of course, right? For water, it's 4.18. Memorize the 4.18. So hopefully we'll get a number that's like not 50. Remember what I said? Water's 4.18, but most things are less, right? So I forget what diamond is. Diamond has a unique value, but generally they're, if it's a metal, it's going to most likely be less than 1 unless it's like lithium or sodium. But glass might be 2, it might be 2.5, but it's probably not going to be 5, and it's probably not going to be 0.1. So 2759 divided by 59.5 divided by 70.6, and it looks like it's about 0.6. I mean, they tell you how many significant digits do they want? 2, which is good because experimentally you're losing a lot of heat anyways. It's not going to be that accurate. So 0.66. Yep. Units are joules over grams over degrees C. And that's going to be C of the sample. Okay. So it's called a basic calorimetry problem. It's more involved than the other ones, but really just in the sense that all you're doing is you're doing it for 2 different materials. Now you're going to see other approaches. If you look at other people's videos or read textbooks or read outs, you can see different approaches. So sometimes, for example, I do it this way. I say, look, M sample, C sample, delta T sample equals minus M water, C water, delta T water. I'll write it out like that directly, right? Because Q of the sample is equal to minus Q of the water. And then you just algebraically solve for C of the sample. And then you plug in all your numbers. That's a different approach. I typically do it that way, but I wanted to show you this way, just kind of to go, step by step so you could see what was happening. So, you read through that material, you're given two masses. If you're given two masses, that means you're probably calculating Q for both of them, right? And then you're just solving for the one that you don't have. But read the question, it'll tell you what to look for. Finding the specific heat capacity of, right? Finding the heat, finding the mass, finding the final temperature. Generally, it's telling you what to do, which is kind of nice. Okay. So there's just one more topic left in chapter 5, and that is the standard heats of formation. Okay, so I'll cover that in a different video. Take care.